All right. Well, welcome. This is Advanced SPARKvue, and today I'd like to focus on introducing you to some advanced features of SPARKvue software. The agenda for today is going to be busy. This is recorded though, so you can go at your own pace, or you may be watching the recording right now. We're going to look at 4 different activities. Now, these activities will span the subject areas, and some of them I hope will be of interest to you in the subject matter. Some will not, but I encourage you to pay attention to all of them because there's something for everyone in each of these activities. I'm using these activities to introduce you to some of the more advanced features of SPARKvue. So we're going to take first a look at the carbon dioxide levels in this room. And this is something I'd like to record over the course of the entire webinar, the entire hour we have together. So I'm going to show you a technique that will allow me to do that without occupying my computer for that entire duration. So we can do some other activities, the second of which is pH of household chemicals. Here we're going to look at the pHs of a variety of household substances, and we're going to look at a technique that might allow us to do this easily within SPARKvue and get us the information that we want in the displays that we want. We're going to use a similar technique when we jump into an analysis of gas pressure and volume. I'd say this is our main activity today because not only are we going to collect that data, we're going to look at how we can analyze it, and then we're going to continue on and see how we can create a file to let students do this and discover this relationship between gas pressure and volume for themselves very quickly by creating a SPARKlab that's designed for their use. We're also going to dive into a deeper feature into SPARKvue called calculations, which you can see allow us to transform data coming from sensors and data that we type in. Then we're going to shift gears and look at a new way to collect data, yet another new way to collect data, one that's needed for analyzing very fast changing phenomena like fast signals in a voltage sensor, or what we're going to do is look at sound waveforms. Finally, at the end of the session, we'll return to that carbon dioxide level data, learn how to bring it into SPARKvue after it's been logged on the sensor itself, and take a look and analyze the data over the past 45 minutes or so. And we'll also talk a little bit more about this technique of remote logging. So that's the plan for today. As you saw in the invitation to this session and the description, we've made some assumptions about your understanding of the fundamentals of SPARKvue. Here's a quick list of those prerequisites that we assume you have. Comfort with connecting sensors and using the sensor data path and the display templates to quickly get measurements of a variety of sensors in SPARKvue. Use of the line graph for viewing data, the most popular display for most sensors, and using the analysis tools that allow you to look at coordinates and slopes and things like that. Also, periodic sample rates and conditions, controlling the default mode of sampling where the sensor periodically collects data at a given sample rate. And saving and sharing files, whether it's SPARKvue files or data files like CSV exported files. Now, there are resources that were also included in the description of this session for getting that knowledge if you don't have it already. So if you're watching this recording, you could pause right now if you don't feel comfortable with these prerequisites and take a look at our SPARKvue Get Started tutorial, which is a very concise 10 minutes, and the Introduction to SPARKvue webinar recording, the prior session to this one done last fall. Now, for those of you who are with us live, Barbara has kindly pasted those in. You'll also see it in the invitation, and I'll add those to the description of the video once it's posted. So let us dive into the first activity here, room carbon dioxide levels. So here's what we're trying to analyze here. What do you think is the current concentration of carbon dioxide gas in the room? And you might answer this for yourself, or if you want to share your thoughts in the chat, feel free to. Do you expect it to change over the next 45 minutes or so? Right now we're in a room that's fairly large. It's our video studio, but Barbara and I are seated here about 10 feet apart and a few feet from the sensor that you can see in the live video feed. So do you expect the CO2 level to change from whatever you think the initial value is? If so, how is it going to change? Up, down? And most importantly, the focus of this activity, how are we going to measure this? Well, we're going to measure it fundamentally using the wireless CO2 sensor. Thanks for your suggestions and guesses in the chat there. We're going to use the wireless CO2 sensor, and we're going to use a special feature of most of our wireless sensors called remote logging. This sensor has a battery in it, that's what makes it wireless, but it also has some memory that allows data to be captured to the sensor itself. Now, typically, and in previous webinars, what we've done is we've connected the wireless CO2 sensor via Bluetooth to SPARKvue and typically use this sensor data path, a popular path for streaming data live to a display like a graph in SPARKvue. But if we think about the next 45 minutes, I need to be using my computer here to demonstrate other activities. So I don't want to occupy my computer just looking at live CO2 sensors streaming from this, live CO2 data streaming from the sensor over the course of the webinar, because we want to do some other things as well. So instead of the sensor data path, what I'm going to show you in a moment is how to set up this sensor for remote logging. And there's a special path for this on the SPARKvue welcome screen, as we'll see now. So let me jump over to SPARKvue's welcome screen. And we're going to take a look at remote logging. And I'll state up front here that this button for remote logging on the welcome screen is a way to both initiate remote logging and to retrieve data from a sensor that has undergone remote logging. So we're going to visit this remote logging button to start and also revisit it at the end to get the data back. So you'll see that we have our wireless CO2 sensor. I'm going to turn it on, and then I'm going to go to the remote logging path here on our welcome screen. And the remote logging path is going to essentially pull PASCO sensors that might be on and put them into one of two categories. The CO2 sensor is in the category here of sensors available for logging. So I'm going to connect to it by clicking on it. It's going to connect to it using the usual Bluetooth low energy. And it's immediately going to say, hey, you're in remote logging. We want to configure the sensor for how it should collect data away from the computer, away from SPARKvue. So with more complex sensors, there are various things we can do, turning some measurements on or off. Thankfully, those CO2 sensor is pretty straightforward. It offers only one measurement. So we're going to focus on a crucial thing here, sample rate. How often or how rapidly should I ask the CO2 sensor to record CO2 measurements? The default is 1 Hertz, and it's important to get the sample rate right, even more so in remote logging, because you're going to see that SPARKvue helpfully tells me that if I collect data at 1 Hertz or 1 sample every second, the memory in this sensor is enough for me to collect just under 16 hours of data. Now you'll notice that as I decrease the sample rate, in this case 1 sample every 2 seconds, it dynamically tells me, well, this would let you go longer. Now there's a caveat here, actual duration may be limited by battery life. We'll talk about that later, but I don't think the CO2 level is going to change very rapidly over the course of the next few dozen minutes. So I'm going to go and maybe sample once every 2 minutes. All right, at that rate, we could get almost 80 days of data in the memory. And again, we'll talk about other constraints like battery life afterwards. Now, I'm going to bring the sensor a little closer to the camera here. This is going to be tough to see due to the refresh rate of zoom, but because I'm connected to SPARKvue right now, the Bluetooth indicator light on the sensor is blinking green. That means I'm connected. This is the same color you'd see if you were collecting data in SPARKvue itself in the usual sensor data path. Now what I'm going to do is I'm going to hit OK, and immediately SPARKvue is going to set the sensor in remote logging mode and disconnect the sensor. So I'm going to press OK. And again, it may be hard to see, but what is happening now is this Bluetooth indicator light on the sensor itself is blinking yellow or amber. Right? That indicates that this sensor is actively logging data to the memory of the sensor, but it has disconnected from SPARKvue. SPARKvue helpfully tells me some instructions for how to retrieve this data later. That's what I'm going to show you at the end of our session. So I'll simply press OK. I'm back at SPARKvue, but there is no connection right now between my computer and that sensor. It is simply logging data for CO2 once every 2 minutes into its built-in memory. So I'm going to set that sensor aside between Barbara and me, and we know that every 2 minutes it's going to be logging another CO2 data point until I stop its data collection. All right. Again, to emphasize that it's no longer connected to SPARKvue, I could close SPARKvue, and in fact, when I retrieve the data, I don't have to have anything but SPARKvue on any device, so I don't need to come back to this same computer. If I wanted to, I could go and Barbara could retrieve this data on her computer with SPARKvue. So any device with SPARKvue could retrieve this data from the sensor when we choose to stop remote data collection. So a little bit more about remote data collection. When is it useful? Well, we've already talked about the benefits of not occupying your computer, and that's particularly helpful when we're doing longer term experiments. 45 minutes isn't particularly long term, but it is going to interfere with the other things I wish to use this computer for in the meantime. So long-term experiments, whether it's in the course of a whole lab period where you have to be using your computing devices for something else, or many days. We're going to see that some sensors enable data collection for days and days and days. The other time it's useful, remote logging that is when you want to do outdoor experiments. You could take a mobile device like a phone with SPARKvue on it. SPARKvue is available free on Windows, on iPhone and Android phones. So you could be collecting data live to SPARKvue from the sensor using a phone, and that's kind of nice outdoors. But still, your phone has to maintain that connection. And if you wanted to do something overnight, I'm sure you don't want to leave your phone there. You might set up something like have a computer inside with the sensor just outside the window, and Bluetooth can go through that over short distances. But you can see the benefits of remote logging if you really want to collect data outside for a long time period, or just want to do an indoor experiment for a long time period. So we're going to revisit this and see if some of your thoughts predictions for the CO2 level over this webinar come true. All right, so let us jump into the next activity while CO2 is logging there in the background. And this is an investigation of the pH of household chemicals. So let me bring my setup over here and give you an introduction. We have a couple of household chemicals here, cola, ammonia, cranberry juice, and we have the wireless pH sensor. And I'd like to show you how we can collect data in SPARKvue for this particular scenario, and then expand it to explain some other scenarios when this approach we're going to take can be useful. So I want you to think, how would you record and display the pHs of various household chemicals in SPARKvue? We're specifically interested in using the wireless pH sensor and SPARKvue. And I'm especially interested in considerations like, what display are you going to use? How much data are you going to collect? As you're thinking about what your response will be, I'll take a survey in a moment. You're welcome to share your thoughts in chat. But I'm going to show you a little bit about the pH sensor. I've taken off the storage bottle from the electrode of the pH sensor while holding the blue electrode itself. And I'm going to set that aside, making sure not to spill it. And then I'm going to rinse off the tip of the electrode here so that I'm rinsing off the storage solution. And then I'm going to gently blot it dry with a tissue so that I'm ready to collect data. So we're going to presume that is all done. How would you collect pH data? So let me pop up a poll here of some answers I've gotten in the past, and whatever your plan is, see if it correlates with one of these three or is completely different from it. So in a moment, a poll will come up for those of you who are live. And the question is, how would you measure the pHs of various household chemicals with the pH sensor and SPARKvue? All right, so one option here, you'll need to hover over it to see the entire response there, but one is graph the pH, record a single run, moving the sensor between chemicals during the run, and then annotate with the graphs annotation tool each section of a run with its chemical name. All right, that's a viable way to do it. Second option here, graph the pH, once again, graph it, but record a separate run for each chemical. Like run number 1 could be cola, run number 2 could be ammonia, and then rename the entire run with the name of the chemical. All right, third option, view pH in the digits display and simply write the values on paper with the chemical name. All right, and then you may have some other plans depending on your understanding of SPARKvue tools. So majority of you have already answered. I appreciate that. Give you about 10 more seconds to share your thoughts on what's closest to your plan for recording the pH of chemicals. Fantastic. So let me go ahead and end that poll, and I'll share the results. All right. And here we can see the most popular answer. 60% of you said, well, just view the pH in the digits display and write it down on paper with the chemical name. And that works perfectly well. That's a very natural way to use SPARKvue and the pH sensor, kind of like you would any sort of pH meter, whether or not you're using software that could record the data. All right. Just under a third of you said graph the pH and record a separate run for each chemical. That works well, especially if you record information in SPARKvue, like renaming the run with the name of the chemical. And others of you, a couple of you had some other thoughts. All right. Margareta asks, do we need to wash the pH meter between different chemicals? Indeed we do, so we'll be doing that between each chemical. That's an important consideration here. One other important consideration that we don't have time for demonstrating here is, how do I know these pHs are accurate? Well, I did calibrate the pH sensor before earlier this morning, so I have confidence that its readings are accurate. And you can do that with just a couple of pH buffer solutions. I'll show you the direction of doing that once we get into SPARKvue. All right, so let us jump into SPARKvue, and let me show you a way that is, thank you. Let me show you a way that is none of the 4 options given there. Let's see if there's any more comments in chat. All right, some good questions about calibration there. Barbara can address those. All right, so normally we might jump in and do sensor data if we want to look at a digits display, but I want to show you that we're going to take control today. This is the advanced SPARKvue course, so we're going to choose build new experiment in many of our activities today because that gives us full control over what we want to visualize. So I'm going to choose build new experiment. What happens when you choose build new experiment? Well, basically we get to design the layout of the first page of our Spark file or SPARKlab. And you'll see kind of like PowerPoint layouts along the right side. There are a bunch of layouts that we can choose from. I'm going to start by using this layout here, the third one down, which basically says there's a little thing on the left and a big thing on the right. I'm going to click on that. And as soon as I click on that, SPARKvue builds page number 1 of my SPARKlab and puts a placeholder of the requested small size on the left and of the requested large size on the right. Now, my pH sensor currently is not yet connected, so I'm going to turn on my pH sensor, pressing its power button, and I'm going to go to the Bluetooth menu, available on any page in SPARKvue, and connect to pH to make sure I have that connection. Now, there's some good questions about calibration here. Again, I calibrated earlier because I don't have a lot of time, but I'm going to go in here and choose a table along the left. Some of you, Kate in the chat there said I'd use a table. All right. Yeah, I think a table is particularly useful because we know we're going to collect just a limited number of pH points, or at least we need only a limited number of pH points. So I'm going to choose a table along the left, and each of these is a potential display that can be put in this space. So I'll choose table on the left. And now that I've connected the pH sensor, I'm going to say, you know what, for the right-hand column of my table, I'd like to select pH. Now, as soon as I do that, as soon as I have any display of pH, I get the live data bar here. And for those of you asking questions that Barbara's answering about pH calibration, if I simply click on that button, I can choose to calibrate the measurement using a couple of pH buffers like these two, 4 and 10 that I used earlier. And she'll share a resource there in the chat about a quick video on how to calibrate it. But having calibrated it, I now have a column for my pH measurements. Now, what do I want in the other column? Well, I think for the majority of you who said you'd view the pH in the digits display, knowing what you knew coming into this, and you'd write the values on paper, you probably would have constructed some sort of table that would have had pH and the name of the chemical. So what I want to do is have a column here with the substance name. And there are a couple ways to do this, but I find the easiest to be the following. I know the first chemical I'm going to measure the pH of is cola. So I'm simply going to double click in the first cell of this column and write cola. And the reason this is a shortcut is SPARKvue says, oh, you just typed some of your own data inside a column of the table. You must want a set of what it calls user data. And it gives it the generic name of user data, but you'll see that pencil icon there allows me to go in and say, you know what, this isn't just any user data. This is the substance or the substance name. And this is categorical data, so I'm going to delete the units because there are no units for this. And at any time I could fill in the rest of these, but since I'm going to do this single-handedly, I'm just going to go down the line there from left to right for those 3 beakers and have cola, ammonia, and juice. But I could do these at any time, and I could even modify them as we go. All right, so we now have the substance names. We have a place in the table for the pHs. And what I want to ask now is, knowing what you know about SPARKvue, if I were to simply hit start right now, what do you think would happen? All right. Well, I'm going to do it. I'm just going to press start, and let's see what happens. Oh, huh. All right, well, I definitely am getting pH in this right-hand column, but I'm getting a lot more pH than I can possibly keep up with because I just want 1 pH for cola, 1 for ammonia, and so forth. Now, why am I getting so many pH values? Well, it turns out I'm getting these pH readings at 5 hertz or 5 samples every second because that's the default way that new SPARKvue files start. It's a periodic sample rate, and this sample rate for the pH sensor defaults to 5 hertz or 5 samples per second, which is way too much time, or way too little time rather, for me to make adjustments and rinse the sensor off as was suggested in the chat. So that's something I need to fix. I wanted to show you what would happen if we just kept things at their defaults though. So I'm going to go into this experiment tools menu, the wrench and screwdriver. I'm going to go to manage runs and delete that last run. I just wanted to show you what would happen if we didn't finish setting this up. So my substance names are still there. My pH values are gone from that errant run number 1. So how are we going to solve this? Well, what would be a good display for visualizing the data in my table, substances and pHs? All right. Well, we've done the line graph in previous webinars. That's a really popular one. Digits certainly could be useful, but I'd actually like to look at all of the values from my table at once. And there's a specialty display here called the bar graph. It looks like this. I want to distinguish the line graph, which is great for measurements against time, as Joss indicates in the chat there. I'm going to use the bar graph instead. And what I want you to notice is, look down here in the lower left. It says periodic 5 hertz. I'm going to press the bar graph. And as soon as I add the bar graph to my SPARKlab, it says, oh, I, SPARKvue, know what bar graphs are for. They're for collecting discrete data points of categorical data. Right? So down here, it no longer says periodic 5 hertz because SPARKvue knew that, you know what, nobody uses a bar graph and wants to record data points in a periodic sampling mode. So I'm going to change it to this manual mode. I want you right now just to recognize that the mode has changed, and we'll talk more about what this means in a little bit. Well, what should I plot? Well, on my vertical axis of my bar graph, I'd like pH. On the horizontal axis, I'd like the substance. But you might be a little puzzled. I don't see substance here, and that's because there are actually two tabs of things that can go into displays. There are direct sensor measurements here in the Sensors tab, which is opened by default, and there's user-entered data. If I go to user-entered data, I can see substance there, and hey, it even begins by filling out the 3 substances I have in the table. So I think I'm ready to collect data now. I've rinsed off my sensor. I'm going to dip it into the first substance, cola, and I'm going to demonstrate, now that we're in this mode called manual sampling, how does manual sampling work? Well, I'm going to press the Start button, and it begins data collection, but it does not begin data recording. That's an important distinction I'll make clear later. But do notice that for the first row of my table, it says, hey, this is cola, and, well, this is live reading. Currently, it's 2.85, 2.7, 2.83. So it's jumping around a little bit, but it's fairly stable. And as soon as it's stable, I want to record that. You can see it's also giving it a live reading here in the bar graph. So how do I say, keep that one value of pH and associate it with cola? Well, there are 2 buttons, the same button repeated. The check mark here is called the keep button, and it's repeated down here. For convenience, it's in both spots. I'm going to press the keep button right here. And what happens? Well, the reading for cola, 2.85 pH, gets associated with it, and it turns black. So this black value of pH tells me that this has a recorded value. You can see it's no longer varying in either the table or the bar graph. So as suggested in the chat, I'm going to make sure to rinse off the sensor between samples. So I'm going to rinse that off, making sure to get the glass electrode clean there with distilled water. I'll blot it dry and put it into the second sample, ammonia. And I should note I've pulled up the cap of the pH sensor storage solution just enough so that it stays out of all of these solutions. All right. And now that I'm in ammonia, you can see that the ammonia value is stabilizing here in both the table and in its corresponding bar of the table display. And since I spilled it there, let me quickly record what's left of that. Go ahead and keep that one. All right. And finally, let me rinse that off. We can see it went down a little bit from the 12 or so. Sorry about that. But let me go ahead and go into cranberry juice and do a better job at holding that sensor this time. And in cranberry juice, we can see it plummets again to a very acidic value, 2.65 or so. This time around, I'm going to press keep down here. And this puzzles a lot of students when they're doing manual sampling, especially for the first few times. They say, hey, I only have 3 substances. Why is it filling out the 4th row? I'll go ahead and rinse my sensor for storage later. So why do I get a 4th row here? Well, the important thing to note is that the value of pH here is still in the color of the run. It's green, not black, which means it has not been recorded. So all I need to do is realize that I have kept the 3 pH values I want, cola, ammonia, juice. I don't need any more. So I'm no longer going to press keep. I'm simply going to press stop. And all of the data, all 3 data points that I collected of pH between pressing start and stop, are recorded here in black in the table and are viewable in the bar graph. So a little bit quickly about this bar graph display, because it might be your first exposure to it. We see we have pH versus substance. You might wonder, why is this little bar down here? Well, we can actually directly interact with the bar graph, but I'm getting my data from the table, so I'm going to turn off this little ghost bar feature. There are tools you're probably familiar with from the graph display, like scale to fit. So I'll scale to fit. I can also manually scale the axes. And there are a couple of nice things about the bar graph. I particularly like turning on the values so I can see each specific pH value for each bar. And there are nice things like statistics tool, which offers the same things that are in the statistics tool of the graph, but does it a little more visually here. So I'll turn on minimum and maximum, and I only have 3 values, so it's pretty obvious. But this tells us across all the data, visually, here's the maximum, 11.86, and here's the minimum, 2.6, which in this case looks like it came from the juice. All right. So that is a quick introduction to manual sampling. I want to talk a little bit more about what's happening here in manual sampling. So we discovered that putting a bar graph into our lab turned on this manual sampling mode, but it doesn't have to only be done automatically. I can always choose the sampling mode explicitly by going into the sampling options, and I can choose to switch between periodic, which is the default for most new files, and manual. And again, this time I got manual because of the bar graph, but in the next activity, I will be turning on manual explicitly here in the sampling options. All right, so sampling modes, periodic versus manual. Let me illustrate this. So we have periodic sampling and we have manual sampling. What happens in periodic sampling? Well, if my file is set for periodic sampling, I press start. the software looks to the sensor sample rate and it records a value at a given time period based on that sample rate. It records all those values until I press stop. All the data between pressing start and stop is a run. Well, by contrast, in manual sampling, what happens? Well, I still press start, and the sensor is giving data points to SPARKvue, but the key difference here is none of these are actually kept until I explicitly press the keep button, that check mark, and say, you know what, that's a point I want. And then I can take all the time I want to rinse the sensor, move it over to the next substance, and I'm ready to keep another data point. So only these pH measurements in black are being recorded. I can vary the rate at which I do this, take all the time I need in order to simply keep the data points that I want. And just like with periodic sampling, when I press stop, data collection ends, and all of the data points that I kept are in this run. In this case, 4 data points would be in the run. I kept 3 data points in my actual collection of pH of household chemicals data. All right, so I've demonstrated manual sampling for pH of household chemicals, and what you probably noticed is that we had 2 sets of data here. We had sensor data, which I put in blue, and we had user data or user entered data that's typed with the keyboard, in this case household chemicals, which I put in orange. I'll give you a moment to scan these dozen common applications of manual sampling, and in each case think about, well, the blue comes from a sensor and the orange comes from something that I type in. All of these are candidates for manual sampling. All right, they use a variety of sensors. And one thing I'd want you to note is I have 2 columns here. Let's take a look at the second bullet in each column. Temperature versus location on arm. Let's say I had a temperature sensor. I put it on the crook of my elbow. I manual sampled one temperature and I wrote a piece of text data that said crook of elbow. And then I put it halfway down my arm and I collected another data point using manual sampling. I labeled that halfway along forearm. And I could do all of these things. So in that case, I have temperature data from the sensor and a text piece of information that I've typed in, location on the arm. Now, how does that compare to the second bullet on the right? Temperature versus distance along arm. All right, well, in this case, I'm still using the temperature sensor, but in this case, I might define my shoulder as position 0, and I'd have a meter stick, and I could say, you know what, at position 0, the temperature is this, and the user entered data here would be a number value, 0 centimeters, and then halfway down the bicep, 12 centimeters. And so forth. So we can do user entered data that is text, those are the examples on the left, and user entered data which is numbers along the right. In both cases, we're using manual sampling. So we're going to do another example here, the last example in the second column, gas pressure versus volume. So let me cue that up. And in this example, we're going to take a look at answering this question. How can we determine the relationship between gas pressure, which is going to be measured by the sensor, a pressure sensor in this case, and volume, which is going to be something that we use user-entered data for. We're going to type this in. This will make a little more sense once I get the visuals here. So here is our setup. So we have the wireless pressure sensor. This can measure pressures from 0 to 400 kilopascals. And what's really nice about this experiment, besides how quickly it can be done, is it includes, the sensor includes everything you need for it. It includes the sensor and a 60 milliliter syringe. Now, we're going to figure out, is this enough with a quick file to determine the relationship between gas pressure and volume? I'm going to begin with the syringe halfway down. So there's 30 milliliters or 30 milliliters of air at room temperature and pressure in there, and I'm going to tighten the syringe on the end of the pressure sensor. So I've trapped 30 milliliters of air in there, and I can use the syringe to increase and decrease the volume. I'll get the pressure corresponding to each volume off the sensor, and I can simply read the syringe readings here and type that in as user entered data. All right. So we're going to do that. That is a key thing we're about to do using manual sampling again, so you'll get another introduction to that. Another key thing, though, is we're going to extend this even further. One of the promises for this webinar is you're going to learn how we can make it easier for your students to get set up and collecting and analyzing data quicker. So we're not only going to set up this file for ourselves to discover this relationship, we're going to talk about how we can set it up for student use. So let us jump back to SPARKvue. I am going to turn off my pH sensor and create a new file. So file, start new experiment. I won't save the previous. And I'm going to return once again to build new experiment. And at the beginning, this is going to look very similar. I think I want a table again, a small table on the left, and a big display on the right. So I'll click on that same template and fill in the left portion with a table display. I need to connect my pressure sensor, so I will turn it on. And then go to the Bluetooth button on the top bar. Disconnect my pH, which appears to still be on, and connect the pressure sensor. All right, so I'll press done here. My pressure sensor is connected. That means it's available for my displays. I'm going to select once again the second column of my table display, select measurement, and I'm going to say that will be my pressure readings, and it reports by default in kilopascals. All right, so once again, there is going to be user entered data. This time it's going to be not text, but numbers. Now, I could simply start typing here. That's how I'm actually going to do it, but if you're interested in the official way, you can press select measurement, and you can go to the user entered tab here, and you can create a data set. But I always use the shortcut, which is if I know the first value, just type it in, and I can redefine the user data directly here in the table. So these are going to be volumes, and this time the units are important. The syringe is marked in milliliters. I'm simply going to use that. And I want to note that SPARKvue has no idea what you're putting here. This is for your own reference, so you could be typing any unit that has meaning to you in any format that has meaning to you. I'm going to type ml for milliliters so that I understand what it is. I'll press OK, and I'm going to go, say, every 5 milliliters. This is something I could fill in while I'm recording, but since I'm doing this alone, I'm going to pre-type it, and I can always adjust it afterwards. Some great questions coming in there. Thanks, Barbara, for responding to those. And thank you for your questions and thinking about what more you want to learn. All right, so I have my volumes. I'm ready to record pressure. I think in this case, our more traditional line graph would be appropriate because I'd like to plot pressure versus the volume. So I'm going to choose line graph and define the y-axis as pressures and the x-axis as this user-entered volume. All right. Now, what would happen if I press start? Well, let's direct our attention over here. This is periodic 20 hertz, so in 1 second, I would get 20 pressure data points because I'm not yet in manual mode, and there's nothing I've done in the SPARKvue file to cause it to automatically go into manual mode. So it's my turn now to manually put it in manual mode. I'll go to the sampling options dial here, and I'm going to switch from the default for most new files, periodic, into manual. All right, and I think I am ready to record here. All right, so I'm going to do this fairly quickly. I know from experience that I can hold it with one hand until just about 15 milliliters. But first I have to extract the plunger of the syringe to get to 60. I'm doing this with a little bit of parallax here, so I might be a little off, but you can see the volumes there starting at 60 milliliters. So let me press start. And again, I have all the time I need to record this first data point. I'll make sure it's stable. I will double check I'm on 60. And again, I can use either keep button. I like to use the one down here when my hands are busy though, because it doesn't move. It's always here. So I'll press keep. The 60 milliliter pressure gets recorded. And I'm going to go down now to 55. Press keep. And you can see I'm getting a live plot of the data on the graph. I'll keep 50. And here's something I often do. I get out of sorts and I collect a data point incorrectly. As long as I haven't pressed stop yet, I can go back and say, you know what, I messed up on 45. I actually double collected at 50. So let me correct that by going back to the pressure cell for that volume of 45. And I can simply press keep again, and it corrects that value. So down to 40. It's getting easier to hold this now as I approach the starting volume of 30. And now I'm at 35. Keep. Now it's simple at 30. 25. Keep. 20. It's getting harder to push this now. And really tough, 15. Keep. All right. Now, if I got someone really strong here, I could say, you know what, I'm going to do 10, and I could simply add 10 here and keep again. But I have all the values I think I need. The graph looks pretty interesting here on the right side. So now that I've checked all the data, because I can't correct the pressures afterwards, I'm going to go ahead and press stop. And again, all of these 10 pairs of data between pressing start and stop constitute run number 1. And it's simply the times at which I wanted to record the data that gets recorded. And these pressures are associated with their corresponding volumes. All right, so let's take a look at this data. Interesting, so it's clearly not a linear relationship between pressure and volume. At this point, I want to start talking about getting our students to do this. And I want them to kind of separate the mechanics of collecting the data and separately do some recording. And I'm planning to give them some instructions on this, but I don't want them to have to set all this up. I want the lab time to be used for data collection and, most importantly, analysis. So let me start to think about how I can take this file and make it into something that I could give to students. I'm going to begin by saying, you know what? I want students to do a specific task on this first page. So I'm going to say rename current page, and I want this to remind them that this is the page that they're going to use to record the data. All right. Well, obviously, if I rename a page to do record and I still have analysis to do, I need another page. So I'm going to come up here and choose this new page button. This is going to insert a new page after the current one within the same SPARKlab file. So if I press new page, it says, oh, you want to construct a new page? What would you like the layout to be? Let me choose something new here, the fourth one down. A large item on the left and two smaller items on the right. And I'm essentially going to replicate, here's page 1. I'm going to replicate this graph on the left. Here's page 2. And while I'm at it, I'll rename page 2 to be analyze. All right, I'm going to put a line graph on the left and essentially put pressure versus volume here. Now, you might say, wait, why does the data look so weird? Well, when I chose pressure for the y-axis, it defaulted to time. So this shows you, in fact, the times at which I recorded these data points. I don't want time, though. I'm going to change the x-axis to those user-entered volumes, scale to fit, and of course, I see the same thing. At this point, some of you may be wishing these lines weren't connected. Well, I can change that. I'm going to go to the graph properties and say, turn off show connected lines. And this is a view that some instructors prefer when students are doing curve fits so that they're not biased by the directly connecting straight lines by default. All right, so I want students to try to investigate whether there's a mathematical relationship between the pressure on the y-axis and the volume on the x-axis. And the way I'd like to encourage them to do that is to look at curve fits. And they might start with a linear curve fit and say, is that good? It's not horrible, but there's some biases and there's a root mean squared error here. But it's hard to tell if it's good if you don't have a comparison. So I'm going to click on this curve fit button and compare it to maybe inverse. Ooh, visually that looks a lot better, and the root mean squared error is definitely a smaller number. Let's look at one other, maybe inverse square. Trends are right, but it looks like it's off quite a bit, especially compared to the root mean squared error of the inverse. So I, as the discoverer of this, would probably say, you know what, I'm going to return to inverse, and I think there's fair evidence here that I've discovered an inverse relationship between pressure on the y-axis, which is y, is equal to some constant over x. What's x? Well, x is the volume. So P equals some constant over V, and this extra tagging on B, it's kind of small. So maybe this is a pointer at Boyle's law, and we might have just discovered something like that. Well, that's the experience I want my students to have. So how can I encourage that? Well, I'm going to go ahead and turn off, I'll leave the curve fit there for a moment to remind myself. I'm going to come over here to this tile that's in the upper right, and I have a placeholder. I can put something small here. I'm going to introduce you to a placeholder I haven't used yet, a display called the assessments display. It's this one here that looks like a couple of checkboxes. And this is basically for a place for me to nudge my students and say, hey, do a curve fit, and there are a lot of curve fits in here. Try these 3. So I'm going to choose a multiple choice question and ask my students in this file, which of the following curve fits is best for your data? And I think I want them to look at the same 3 that I looked at, linear, inverse, and inverse square, and assess which one is best for their data. Now, if I knew the right answer, well, for my data, I know the right answer, but I don't know it for theirs, so I'm not going to define any of these 3 to be right. I'm simply going to give students the opportunity to say it's this one, or it's this one, or it's this one. I'm going to check my spelling, which of the following curve fits is best for your data, and I'm going to lock this, so I can't change it and students can't change it. All right, so this is a way to encourage students to say, hey, I want you to do the following in this file, and here's a suggestion for the things to try and assess. Now, here's another display I could use. I have a placeholder in the lower right. I might say, you know what, this is a place for text, and I could put instructions to my students for further analysis, or they could use this to write their own notes. All right, I won't actually fill in what I want there, but there are a couple possibilities in this note box. So we're beginning to see that the displays in SPARKvue aren't just for data. All right. So I think we have the beginning of a lab here. It still needs supplemental instructions to my students on how to collect data. I can deliver that in a variety of means, on paper, verbally, in a video. But I think we're taking shape here on a file that I might want to give to students. So let us turn our attention now to getting this ready for students. Now first, I don't want to have to collect this data again for myself, so I'm going to go and save this file once for my own use. And I'm going to save it, say, to my desktop, and I'm going to say this is gas pressure versus volume with data, because I still have the data in this file. All right, and now I'm going to say, what would it take for me to give this file to students to give them a jump start so they can focus on data collection and analysis instead of the mechanics of SPARKvue? Well, I have a question for them. I have a place for notes. I don't want them to have a fit already here. I want them to turn it on. So I'm going to get rid of my fit. All right. And I'm going to go back to page 1 here. And of course, I want them to collect their own data to make their own discovery. So what I need to do is delete this data from the pressure sensor without deleting the volume data. And it turns out user enter data by default doesn't get deleted when you take the following action. I'm going to go to Experiment Tools, Manage Runs, delete all runs, there's only one, and press done. And now if I look at it, I think this file is probably something I could hand my students. It has the sampling mode set to manual. It has some volumes pre-entered. They could always change it if they want to. And it's ready for them to simply connect the sensor, press start, record the data, and then walk through this collection and analysis. So I'm going to save this file once again using Save As. And we have different names for this. I could call it gas pressure and volume, config file, or template, or just leave it off, just gas pressure and volume. This, of course, is a SPARKlab. So what I could do is just give this to my students, distribute it via email, file servers, online storage, however you send your SPARKvue files to students. They could open this up, connect their pressure sensor, collect data in manual mode, and do their analysis quite rapidly. All right. So I hope you've seen how we can quickly set this up for our own use in manual sampling, and then extend it so that it's ready for student use. Now, I'm actually going to return to my data file because I want to extend this a little bit. So I'm going to go and open up the data file because there are a couple of more advanced SPARKvue things that I think are worth discussing in the context of the data I've already collected here. So you'll recall that we've discovered that pressure versus volume appears to be an inverse relationship. And many instructors love to have students look through the variety of curve fits and pick the one that fits best visually, root mean squared error. Other instructors say for pedagogical reasons or test practice reasons, I want my students to make every relationship linear, and then they can just focus on using linear fits, which on some tests are the only thing you can do with a ruler. So let me show you how we can take this relationship that we suspect to be inverse between pressure and volume and actually linearize this, this graph. So in order to linearize it, I know I need to take the inverse of either pressure or volume. Either one would work. I'm going to say I want to take the inverse of volume and graph pressure versus inverse volume and see if that's a straight line. Because if this is indeed inverse, it should be a straight line if I plot pressure versus inverse volume. So here's an introduction to a very powerful tool in SPARKvue. It's called the calculator. And there are a couple ways to access it. I'm going to show you the most general way, and that's to go to the experiment tools once again. And you'll see that there's a button here for calculated data. This opens up the calculator, and the calculator is kind of a tool that lets you take data and transform it into other data. So here's the syntax. Here's how it works. If my goal is to calculate a set of data which is inverse volumes, I can create a relationship almost like I'm defining a relationship, an assignment in computer programming. And the output of this calculation is going to be on the left side of an equal sign. I'm going to call it INVVOL. And on the right side is going to be the actual mathematical transformation. Well, how do I get inverse volume? A couple ways to do it. I can do to the -1 power. I could say 1 divided by. And here I'm not going to enter a specific volume. I'm going to enter the whole set of volumes. How do I access that? Well, there's a big orange measurements button here, and this gives me access to all measurements, whether coming from sensors or user entered. The volume is user entered. So I'm going to tap on that, and you'll notice that it says, okay, This is inverse volume. It's going to be defined as 1 over every single volume measurement that SPARKvue has. If I want to, I can define the properties while I'm still on this line and say, you know what, the units for this is going to be kind of an odd unit, inverse milliliters. But if I want to define units, I can do that. Most crucially, though, what I want to do is say return, and there are no complaints about this expression. So I'm going to press done and OK. All right, so I created a calculation. I have a new set of calculated data. Well, I need to now say, you know what, I want to show that data in this graph. Specifically, I want to change the x-axis measurement from volume to inverse volume. All right, and now when I scale that, you can see that because I'm plotting pressure versus inverse volume, I now get what is quite clearly a linear relationship. So if you're into linearization, it's really nice to know that you can do that by transforming data in the calculator of SPARKvue. There is another way to get to the calculator. You can simply have a place, let me add a column here, and you can say, you know what, I want this to be a calculation. You can choose select measurement, user entered data, and create a new calculation. This brings you back to the same calculator where it turns out you can add additional lines. So some instructors like to say, I want my students to understand that for an inverse relationship, you can multiply the two variables together and it should be a constant. So I'm going to say, here's a new line, new calculation, pressure times volume. All right, hit done, okay. And notice it fills that in. So I now have a column in the table, which just could be just as well in the graph, any display of that calculation. One final thing to note, what's really powerful about the calculator is you don't just use it after the fact. If I hit start right now, notice that these calculations, these transformations are happening live. All right? So it can do the transformation with live data as well as prior runs of data. All right, so that was a lot of information, but hopefully you've seen how we can discover the relationship between gas pressure from a sensor and volume, a numerical value from the syringe, and more importantly, set this up for student use and transform the data if we want to do something fancy like linearize or transform data, whether it's measurements from the sensor or user data. All right, and we've done all this with build new experiment because that gives us the flexibility to design our own pages. I should note while I have the pressure sensor connected that there is a shortcut if you want to do this specific experiment. If you go to sensor data, something like the first page is already set up here in the quick start for Boyle's law. All right. So before we return to CO2, I have one more important activity here. It's a pretty quick one, literally quick. And this is, can we use a wireless sound sensor to view sound waveforms? What do sound waveforms look like? What does the pressure variation look like if I whistle or if I strike a chime? So let me switch the equipment here. And the second thing we want to do is determine, once we've found a waveform, can we determine its frequency if it's a simple waveform, or can we do something more complex like determine various frequencies in a more complex signal? So for this, we're going to use the wireless sound sensor. And I have a set of chimes here that should give us some clean signals to look at. All right, so we're going to learn some new things here. And this is one of the things today that you can't do any other way. So I'm going to first show you what you can't do with the things you probably know already. I'm going to turn on the wireless sound sensor and turn off the other sensor, pressure here. And I'm going to go down the path that would be natural to start at, sensor data. And with my wireless sound sensor on, I will connect to it. And it would be natural to say, all right, I'm looking at sound wave. Let me look at it in a graph. All right. And I did have a little remnant of a previous sensor, so let me just start that file again and reconnect. What I want to show you is the default sample rate for the sound sensor. So once again, sensor data, I'll reconnect to that wireless sound sensor. I had a prior sensor connected, and that's why the sample rate didn't default to the sound sensor's default sample rate. So back there to graph. What I want you to note is 1 kilohertz. So this sound sensor in the sound waveform view knows that sound waveforms are varying, sound pressure level varies quite quickly, and it has 1,000 samples per second. So that's the default sample rate. Let's see what happens if we plot the sound waveform versus time at 1,000 samples a second. I'll go ahead and stop talking and hit the chime once I've started recording. And I'll stop. So 4 seconds there, that's 4,000 data points. Let's zoom in a little bit. I do get a decrease in volume, it seems. The peaks are lower over time, but when I zoom in here, this doesn't look very clean. It doesn't look very promising. I might be getting something happening here that I'm not sampling fast enough. Might be aliasing. So let me go in here, sampling options. I can increase it to 2 kilohertz. Let me try that. All right. I'll tell you on some machines at this point, I'll say I can't keep up. On this machine, it happens to do it. But still, I'm not getting good results. This isn't the clean signal I'm expecting from a clean chime. So let me tell you that this isn't the right approach, because even at 2 kilohertz, which is the maximum I can go to in this mode, that's not fast enough to be measuring variations in signal that themselves may be happening at kilohertz speed. So I'm going to go back to Start New Experiment, and once again build a new experiment so I'm in control, and introduce you to a display that's tailor-made for this type of analysis. So I'll create a full page display, and because I have the wireless sound sensor connected already, a key point, you'll notice I have some displays which you may never have seen with other sensors. This is called the scope display, and that's where I want to start. If I define the x-axis of the scope display to be the signal coming from the sound sensor's sound wave sensor, notice this. Look down here. There are a couple of things that have changed in the lower left. It says scope. So my mode has automatically changed to what's called scope mode. And I've accessed a sample rate at 20,000 hertz, 20 kilohertz, faster than I could have in the graph display. So I'm in a new mode called scope that was initiated because I have a scope display. And it's at a very high sample rate. So let's see what happens here. I'm going to hit start, hit the chime, and then stop talking for a moment so we can get a clean signal. That's quite promising. I'm seeing a variation that I kind of expect, at least when I'm not talking. So let's open up the toolbars here, and you're going to see a lot of the same tools as you're familiar with for a line graph. A couple new ones, but there is scale to fit and annotations and things like that. But let me introduce you to a couple new tools. The one I want to start with is this trigger is going to let me see it not jump as much. So I'll hit trigger on. I could increase its level or decrease it. I'll put it around 0 still. So it's going to trigger whenever the signal goes up across 0. And I'm going to hit the chime again. That's nice because it's no longer jumping left and right. It's always triggering on the up part of the signal. Now, why in the world can it sample at 20 kilohertz now? Well, that's because it's not actually recording any data. It's just monitoring the data and taking 0.0035 seconds worth of data as fast as it can at 20 kilohertz and putting it on screen, and that data just goes away. So what I'd like to do is do one more modification. Let me look at the sound waveform. That's looking pretty good, but it's a little jagged. So I'm going to press this button right here to increase data points. And what I want you to notice is the curve gets smoother and my sample rate automatically increases here. So I think that's probably better. And how do I capture a sound wave once I like it? Well, I'm going to press stop as soon as I have what I want. All right. And as soon as I press stop, it captures this last frame. It's a run, and I can now do analysis on it. Like, for example, turn on a coordinates tool to find the time of a peak, turn on the delta tool and find the time between peaks to determine the period and thus the frequency. All right. So scope is great for taking snapshots of fast acting signals like this. Just to show you, we could continue. I'll press start again. There's a higher chime, and I can visually compare things like amplitude and frequency period between those different sounds. Now, I could manually determine the frequency from the period here, but what I'd like to do is show you there's a tool built into SPARKvue to do that automatically. I'm going to create yet another new page, make it full screen, and show the other display that comes up when you have a wireless sound sensor or a wireless voltage sensor, any sort of sensor that's good for fast signals. This is called the FFT, or Fast Fourier Transform. Notice its x-axis is frequency. So if I put the sound wave in here and press start and hit the chime, and then hit stop, this is essentially a spectral analysis or a fast Fourier transform of the scope signal, and it automatically determines the components of frequency. This tells me that there's a very strong frequency component in that signal at 2,588 hertz, which is probably the frequency of that. Now this gets really interesting when you start to have more complex signals. I'm going to press start again. I'll go back here to the scope, and look how messy this gets. All All right, that waveform looks like it's composed of different waveforms, but the FFT will decompose that and show me that these are the peaks from each of those separate chimes. So FFT is really useful when you have fast signals and want to decompose it into its frequency components, or even for things that are happening mechanically more slowly and you want to look at, say, resonant frequencies. All right, so that is a quick intro to sound waves. We are going to jump back here to remote logging. We have only a couple minutes left, but thankfully this will take only a couple of minutes. Barbara, thank you for continuing to answer all those great questions I see in chat. We're going to return to the wireless CO2 sensor. What has it been doing? Well, if we zoom into the sensor here, you can see perhaps that its Bluetooth light is still blinking yellow. That means it is still logging data. Remember, it's been logging at 2 minutes sample period, so one sample every 2 minutes. Let's figure out how to retrieve that. I'll go to SPARKvue, Start New Experiment. I'm going to go to that same remote logging button. And at this point, I need to focus on the sensors with data to select to download. But something key has happened here. The sensor has turned its radio off so that it can dedicate its power to logging. There's a nice reminder here. Briefly press the power button to awaken sensor. I will press it, at which point it is still blinking yellow, meaning it's still logging data, but it's also blinking red, meaning its Bluetooth radio is turned on, and that makes it accessible to select down here. I will connect to it. And it says, hey, you've connected to a sensor with logged data. What would you like to do? Well, I'm going to download the data, but just to keep things clean, I'm going to say, you know what, after you've downloaded it, go ahead and delete the data by selecting that checkbox. I'll download it. It asks me how I'd like to display it. I'll choose the graph template. And when I scale to fit, we can see, looks like I had maybe a bad first data point, but over the course of these 3,000 seconds, it looks like the CO2 level has crept up a little bit. I might ask, well, what's the rate of increase? I could turn on a linear fit and see that it's kind of hard to interpret in seconds. So let me change the time units from seconds to, say, hours. And this tells me that over this time period, it looks like the average increase was 92. That's parts per million of CO2 per hour. So a little bit of increase with 2 bodies in here respirating. Okay. Now, this wasn't very long, so I know when I started, but one neat thing about remote logging and the graph is that I can do the following. Not only can I change the units of time, I can actually switch to a different mode called date and time. And at this point, it actually tells me I started at 12:40. This is where I am Pacific time, and I ended just before 1:30. So this is a neat way to see the actual time at which phenomena occurred, which can be really useful, say, if you're logging weather parameters outside. You want to see when it was midnight, when it was noon. So this switch from date to date and time can be really helpful. Well, fantastic. So we have reached the official end of time here. If you need to leave, I want to thank you so much for joining us. I'm going to wrap up with a couple extra slides here. They'll be in the recording, so if you need to leave, you can always review the recording. And we'll wrap it up here, and then we'll open it up for those of you who are live with some open Q&A. So stick around if you want to learn a little bit more wrapping this up. I'm going to talk very briefly about remote logging. Which sensors do it? How long can they log? I saw some great questions earlier. If you go to the product page for each of our wireless sensors, you're going to see it either has logging or it doesn't. In the case of most of the wireless sensors, these are the white sensors that use BLE, most of them can do remote logging. There are some exceptions. You can't remote log with a smart cart or a photogate or a motion sensor, but most of them you would want to do logging with, you can. And that includes sensors for the environmental measurements, like CO2, temperature, weather. It also includes some things that are kind of fun, like accelerometers. So if you want to take an accelerometer in an elevator, as our colleague did recently. All right, so which sensors can log? Most of the white wireless sensors. How to find out? Go to their product pages. How long can they log? Well, as I alluded to earlier, there are 2 considerations. The memory consideration, and you can see in the case of these 2 sensors, CO2, they can both record over 55,000 data points. Now that's going to go up or down based on the memory, number of measurements. But the nice thing is SPARKvue told me how long it could log in terms of memory when I set the logging parameters. The thing that SPARKvue doesn't tell you is how long is the battery going to last. It kind of opts out and says, be cautious. But our website basically tells you, here's how long you could go logging on battery power alone with a fresh battery or a fully charged battery. So I could do 18 hours for the CO2 sensor. The wireless temperature sensor is a lot less power hungry. I can do 35 days on a fresh coin cell battery in that one. So various amount of times. If you're sticking around, let me open up one file here and show you. I did log CO2 in the office last year for just over a week. And here is that data. You can see a Wednesday through a Thursday. I'll leave this up and you can start looking at some trends. I encourage you to share your observations as we go through here. But the first thing you're going to ask is, wait, this is CO2, which only logs for 18 hours. How did you do that? Well, I was in the office, so I simply connected the sensor to a little USB charger connected to the wall, and I ran it off of wall power that entire time. So I didn't have to rely on the 18-hour battery of that particular sensor for logging. So I'll leave that up there. If you have any observations, please share them. You can see it's particularly useful to be able to look at days of week and times of day. You might even notice when we have lunch as a group here and whether all of us are in the office on certain days or not. But you can see some power of remote logging, and again, it didn't occupy my computer. If you want to learn more about remote logging and a really exciting opportunity to map the data using GPS data, join our colleague Roger on April 12th for a webinar at the same time of day, and you can sign up there at pasco.com/pd. All right, so what did we learn today? Well, sampling modes. We reviewed periodic, which is the default. It's great for getting data live in SPARKvue, or as we learned, for logging data to a sensor's own memory if you want to collect away from the computer. We learned about manual sampling. It's great for user-entered data, discrete events, and entering that data, whether it's categorical text data or numerical data. And finally, we learned that we can use FFTs and scope displays to trigger the scope mode, which is great for monitoring fast-changing measurements. All right. We also got to look at some new displays, new to most of you, including bar graph display, text boxes, assessments, scopes, FFTs, and there are a lot of other displays in here that will show up only with specific devices. Popular ones include signal generators and specific panels for controlling smart card accessories. All right. So I'll close it down here. If you have any questions, want to contact either your local PASCO rep worldwide or get in touch with PASCO's technical support, feel free to scan this or go to pasco.com/support.